The next reaction we're going to see is called dihydroxylation. Now, a dihydroxylation reaction also occurs in multiple steps, and the net effect of this reaction is the addition of two alcohol groups for dihydroxy across the alkene bond. The word diol means di for two and all for alcohol, so we add two alcohols. Since these two groups are the same, like we saw in halogenation, there's no Markovnikov or anti-Markovnikov addition because they have the same priority as each other. But we do need to consider their stereochemical outcome. And here, the two alcohol groups will be added syn, or on the same side. Now, the way this reaction is done is by using a couple different reagents. The first reagent is osmium tetroxide, most commonly, or potassium permanganate, less so, with some sort of dilute OH minus. This OH minus is typically delivered as KOH or NaOH, as these are our most convenient sources of base. Now again, you'll notice the addition of two OH groups here, and the transformation of the alkene to the alkane. So we have no Markovnikov versus anti-Markovnikov, but we have syn addition. So let's take a look at how this happens. So the steps of a dihydroxylation and the mechanism of is remarkably complicated. And so you're not going to be asked to be responsible for the mechanism at this level of organic chemistry. It does occur as a concerted reaction for the first step. In other words, everything happens at once. We make a 5-membered ring. And that happens with either the osmium or the KMNO4. The second step of the reaction is hydrolysis with some dilute base to give the diol. So again, you're off the hook for the mechanism, but it does help to know that we have a first concerted step and a second hydrolysis step. Keep in mind that the mechanism is really complicated, so you don't need to know it. But you do need to watch out for the stereospecificity of the reaction, which means that this reaction will maintain the geometry of the reagent. This means that for alkenes, most commonly, cis double bonds will stay cis and trans double bonds will stay trans. Let's predict the products of a couple of reactions so you can see this in action. So here, we're going to be asked to follow through with these examples. We've seen these alkenes before, where we have a trans alkene here and a cis alkene here. Should we have addition of the KMNO4 and base across this trans alkene, we should show both syn addition of the diol and maintenance of the trans configuration of the alkene. What this will look like is like so, where we show the diols being added on the same side like so, and the two methyl groups of the alkene being shown like so. So again, you'll note we have syn addition of the alcohol and the two methyl groups remain trans from each other. Let's look at the syn addition as well. So if I have the cis alkene, I have the two OH groups, I get here, and I show the two methyl groups like so. You'll notice that we have some chirality here, and so I'm going to want to draw the other stereoisomers. Now, if I was to draw this stereoisomer here, and I'll draw it out for you, these would actually be meso compounds, which you'll remember. And enantiomers of meso compounds are the same thing. These are identical, and so it doesn't matter which one you draw. But with the example up here, it would. And so allow me to draw them like so, where we have the methyl here, we have another methyl here. And here you'd need to show both. So this top here, you need to show both structures because they're different than each other. But the bottom one, since they're a meso compound, and enantiomers of meso compounds are the same, you don't. So dihydroxylation with its complicated mechanism is a reaction that you need to be able to predict the product for. We don't need to worry about Markovnikov versus anti-Markovnikov, but we do need to worry about the syn addition of the diol. Last, you need to worry about the stereospecificity of the reaction, which is to say that cis alkenes remain cis in the product and trans alkenes remain trans in the product as well.